Thank you very much for that introduction, Simon, and kia ora koutou. Thank you all for coming along. And it is the first morning, it's sort of a Monday morning, isn't it, after a long weekend. So a double thank you for being here. My brief for this presentation, and it's great to know that Rod Carr spoke a few weeks ago, and yes, the final advice will finally be public tomorrow. You might say it's the bad news. The draft advice was about 200 pages, the final advice is about 400 pages, but it's beautifully laid out and it looks fabulous in my opinion. And yeah, there's a lot more explanatory text, I think, is why it's longer. A lot of the submissions talked about why this, why that, why is the Commission acting this way, and so on. So hopefully we've spelled it all out. Anyway, for today, to really go through some of the basics of the science, I think, as well as talk about what's happening, what are the consequences, I suppose, for Aotearoa, and what role does the finance sector, the business sector, government sector play in doing what we need to do, reduce emissions of greenhouse gases. So my title slide has an image taken off the Radio New Zealand website a week or so ago of a river in flood in Canterbury, now about 10 days ago, and already researchers, colleagues at NIWA and the Met Service and elsewhere are looking at this event and starting to think about what fingerprint climate change had in this event. Did it mean there was more rain falling into the rivers than you would expect otherwise? Has it increased the likelihood of this kind of event happening again, and so on? We'll have to wait a while to see what the numbers are on that, but yeah, the work's underway. And I've just realised, do I have to ask you to click? Okay, I've got quite a few animations, so okay, click please. Okay, so I thought, just hold on. You'll be clicking quite a lot, I'm afraid. We can't have that over here, can we?
No.
No, okay, all right, fine. So I thought, just to make sure we're all on the same page, to start off with the absolute basics, what does drive climate change? So click. So all of the energy in the climate system that drives the weather, the clouds, the winds, whatever, and allows life to exist on the planet comes from the sun originally. So the sun is the ultimate biggest player in the system. But crucially for climate change, it's important to understand that the atmosphere is essentially transparent to sunlight. Some of it gets reflected, a bit does get absorbed into the ozone layer in the stratosphere, but other than that, the rest of it shines through the atmosphere. The carbon dioxide, the oxygen, whatever, doesn't really see sunlight at all. So it reaches the Earth's surface and it warms the Earth, not the atmosphere. So click. So the Earth warms up and it radiates energy to space, just like the sun does. But because the Earth's a lot cooler than the sun, it radiates energy that's much less intense, has a longer wavelength basically. And this is what we call infrared heat radiation, what our bodies radiate, rather than visible light and ultraviolet, which is mostly what the sun radiates. And the atmosphere is not transparent to this stuff. So there are gases in the atmosphere which we've come to know as greenhouse gases, carbon dioxide, etc., that are very, very good at absorbing this kind of energy, and that's what they do. So the atmosphere warms up and it radiates energy in all directions. Eventually enough gets out to space to roughly balance what's coming in from the sun. But in the process, a lot of that energy is re-radiated back to the Earth's surface. So the Earth gets warmed twice, once by the sun and also by the energy coming out of the atmosphere. And having these gases in the air is very like having a blanket on a bed at night. You put a blanket over yourself at night, some of the energy from your body is captured by that blanket and held underneath, and you're warmer than you would be otherwise. Same deal with having these gases in the atmosphere. It's like having a blanket over the whole Earth. And as you all know, if you put a second blanket on yourself in bed, you get warmer. What's underneath the double blanket is warmer than where it was before. And if you put more of this stuff in the atmosphere, what's underneath also gets warmer. It's like having a thicker duvet over the Earth. And so that's what's happening at the moment with climate change. That we're layering the Earth with a thicker blanket of greenhouse gases, basically. So click. So yeah, these are the two ways to change the climate. If the climate's changing, one or both of these things have to be happening. The amount of sunlight falling on the Earth has to be changing, or the amount of greenhouse gas in the air has to be changing. And in the past, through the ice ages and so on, usually it's both of these together. But at the moment, the sun is not getting brighter. In fact, it's getting a little bit dimmer. But the amount of greenhouse gas in the air is going up hugely. So, next slide. Oh, can you go up? No, up. Back. Oh, you can't get rid of that 230 years? Okay, not to worry. All right, so this is a graph of how carbon dioxide has varied in the atmosphere over the last, over the last 13,000 years or so, since sort of coming out of the last ice age. So in the depths of the ice age about 20,000 years ago, carbon dioxide was down at about 180 parts per million, and that's the vertical scale there. It got up to about 280 parts per million about 4,000 or 5,000 years ago, and that's taken as the pre-industrial level. And since we started burning oil and coal, Europe in the 1700s, the Industrial Revolution, the amount of this stuff in the air has gone up dramatically, exponentially actually. So a couple of reasons for showing it like this. Often you see a graph of carbon dioxide and it's the last 50 years or whatever, and you can see it going up, but it doesn't look very dramatic. But it's not a human lifetime the Earth operates on. It's the Earth's timescale is much more like this. It's thousands of years. So if you want to melt a big ice sheet, for instance, it would take about 10,000 years. You want to change the deep ocean circulation, that takes a few thousand years. If you want to raise or lower the amount of greenhouse gas in the air, carbon dioxide, through the usual means the Earth operates on, that takes thousands or maybe even hundreds of thousands of years. So we've made a change to the composition of the atmosphere in a century or two that's, it's happening hundreds of times faster than the normal processes. And if we stopped emitting today and waited for that spike to come down again, that would take about 10,000 years as well. So we've locked in, we have a new climate now that's going to be around for many, many, many human lifetimes, forever in terms of our sort of time horizons basically. And if we do a click and see that, it's been about 260, 270 years since this experiment started. The first half of the rise took about 230 years, and click. The second half of the rise, click, has taken 30 years. I'll just tell you the answer. Hey, there we go. So, 30 years ago is when the Intergovernmental Panel on Climate Change got started. It's when the United Nations Framework Convention on Climate Change got started. All the negotiations that led to the Kyoto Protocol and the Paris Agreement have been going on for about 30 years. And in that time, the global economy, global energy production, the global society has made the problem twice as big as it was back in 1990. So we're now at a point where it really is an emergency, We really have to stop this spike getting higher if we want to stop climate change. And that's the other message here, that this stuff that builds up like this, it spikes like this because it stays around for centuries. Part of the carbon dioxide we emit today will still be in the atmosphere in 1,000 years, 5,000 years. Most of the carbon dioxide that James Watt and co emitted when they fired up their steam engines in the 1700s is still in the air today. We're breathing it, most likely, part of it. So this stuff, because it stays in the air so long, this is why climate scientists concentrate on carbon dioxide, and that's why the Zero Carbon Act focuses on net zero emissions of carbon dioxide, but only just a reduction in methane, because methane only sticks around for 10 or 15 years, and once you turn down the tap, it starts to decrease in the atmosphere quite rapidly. If you want to stop this stuff building up more, you've got to turn the tap right off to zero, and then you might have to think about how do you take this stuff out of the atmosphere. The natural processes take a very long time. And another click. So the amount of the stuff that's in the air now is about as high as it's been for 3 or 4 million years or so. So this is, before our species evolved. So this atmosphere we're breathing today is completely unknown in terms of humanity. Maybe the climate has been a bit warmer than it is now in the past and over the ice age cycles, but the actual atmospheric composition hasn't looked like it does today since the mid-Pliocene, since well before we have been around on the planet. Okay, so this is our thicker blanket of greenhouse gas on the Earth, and when you look at temperatures, you see that they're rising because that's just how it has to work. You put more of the stuff in the air, the surface temperature has to go up. So this is annual average temperatures from the NASA group in New York. All these global centres, the numbers look much the same really. So going back to 1880, and the vertical scale is temperature change. The zero line is the best estimate we have of what the pre-industrial temperature was, which was just the average temperature before 1900. So it's only 20 years or so on this record. And you can see, well, it's getting warmer, that's pretty obvious. There's ups and downs because of El Niños and volcanoes and whatever, but the trend is pretty obvious. And the last 6 years, the last bar there is 2020, we're all more than a degree above pre-industrial. So it's warmed up quite rapidly, and we're starting to get reasonably close to some of these thresholds that are talked about in the Paris Agreement and the Zero Carbon Act. And if you click, you'll see, well, all it says is the top of the scale is 1.5 degrees. So there's not a heck of a lot of headroom there. We're getting close in terms of just the average temperature. And I think a report came out just last week from the UK Met Office saying there was a sort of an even chance or 40% chance or something of an individual year being more than 1.5 degrees above pre-industrial over the rest of this decade or over the next 5 years or something. That seems quite possible. And another click. If you look at the last century, going back to 1920, and just cut it into 250-year bits and look at the trend, well, again, I can just tell you the answer. The first 50 years, the trend is about, yeah, there we go, just a bit less than 0.5 degree per century. And for the second 50 years, if you click again, it's pretty close to 2 degrees per century. So the rate of warming has gone up a lot as we've dumped more and more of the stuff more quickly into the atmosphere. So that sort of rate of warming, unless we take significant action, is the sort of rate of warming we'd expect for the rest of the century. So we could be at 3 degrees above pre-industrial by the end of the 21st century without too much trouble, actually. Okay, and you warm the climate, I mean, that's all very well. It's 1/10 of a degree warmer than it was 10 years ago or whatever. That's not how we experience climate change. It's through extreme events, right? So a warmer atmosphere makes it easier to click the mouse and get evaporation happening more efficiently. It's going to come on the screen. There we go. And you get more droughts more often, and the droughts tend to happen faster and be more severe when they happen. And warmer conditions and drier soils, drier vegetation leads to greater risk of fires, and hopefully a little picture of a burning guest house will appear on the screen. This is from California from last year. And so, you know, fire danger and drought conditions and heat waves, of course, are some of the most obvious consequences of a warming climate. But for rainfall, it's kind of perverse that not only do you get more droughts, you also get more floods. And when it rains, it tends to rain harder. And the reason for that is because the amount of moisture in the air, water vapour, is one of the most important greenhouse gases. The amount of moisture in the air is purely a function of temperature. As you warm up the atmosphere, you get more evaporation, you get more water vapour in the air. So when you have a way to get it out, such as a storm or air flowing over a mountain in the South Island, for instance, you tend to get more water falling out, so you tend to have a heavier rainfall event. And that's why in my first slide I said this event in the South Island a week or two ago is most likely to have some kind of climate change signature because it's already warmer and there's already more moisture in the air. Okay, so next slide. All good? Yeah. So this is a graphic from the special report on climate change and land that came out from the IPCC just a couple of years ago. Just to make the point that, so there's two lines here, again it's temperatures going back to the mid-19th century. The lower line, the dark one, is the global average temperature, and it's a bit above 1 degree now. But if you just average temperatures over the land surface globally, we're already above 1.5 degrees of warming, and one year at least, as 2016, was getting close to 2 degrees. And so water takes a lot more energy to warm up than land does. So the land surface warms faster than the oceans do. So when you average both, you get a slower rate of warming. So that's just to illustrate that. So if we're just thinking about land, we're already above 1.5 degrees. You know, again, the idea that we really need to get on and take action. And that point that the oceans take a lot of energy to warm up is an important one, because the oceans cover nearly 3/4 of the Earth's surface, and the oceans are actually soaking up most of the heat that's coming from this extra greenhouse gas in the atmosphere. So only about 2% of the heating has gone into actually warming the air itself. Over 90% has gone into warming the oceans, which is good news for us, because if it had all gone into the atmosphere, temperatures would already have gone up somewhere between 40 and 50 degrees, we'd all be dead. So it's slowing down the rate of warming we experience quite a lot, but it is locking in change in the ocean in various ways for many centuries into the future. And if we click, one of the main ways that the ocean's changing is because it's getting warmer, it's getting deeper. You know, like pretty much everything, you heat water, it expands. So the oceans are expanding, and of course they can only go upwards. So sea levels are rising globally and have been doing so for quite some time now. If you look at the satellite record starting in 1992, and just fit a straight line through that. So the vertical scale here is global mean sea level, the change in millimetres, with quite small numbers. The rate of change is 3.5 millimetres per year in that roughly 30-year period. And if you look at the last 10 or the last half of that record, we're over 4 millimetres per year, I think. And if we click the arrow, we'll see that that rate is more than double. It's getting on for triple what the rise in sea level was in the first part of last century. So because the oceans are expanding, and really because ice is melting and there's just more water in the oceans now, that's what's driving the acceleration of sea level rise. It's the ice melt, really. So if we click again, have a look at that. So this is change in the mass of ice on the two big ice sheets. Antarctica on the left, Greenland on the right. And Antarctica can divide into the West and the East Antarctic, but anyway, taken together, that's what this graphic shows. Going through to 2019, and again, this record is pretty short. It's a satellite record from 2002. And what we see, the vertical scale here is change in mass in gigatons and billions of tons. Each tick's 1,000 of those, so each tick's 1 trillion tons of ice. So Greenland in that time since 2002 has lost, getting on for 5 trillion tons of ice. And Antarctica's lost about half that much, something like 2.5 trillion tons of ice. So between them, on the order of 7 trillion tons of ice melted off the big ice sheets since 2002. And the rate of this melting is going up. So that's largely what's driving the increase in sea level. And the big question, really, the big unknown, is how much more of this ice is going to melt, and where are the thresholds for irreversible melting. One of the things we do know reasonably well, I think, is that when you get to about 2 degrees of global warming, and this is based on the geological record and on ice sheet modelling, you do kick in irreversible melting of the West Antarctic ice sheet at least, which would raise sea levels by somewhere between 3 and 4 metres. Greenland would probably be heading south at the same time. The East Antarctic is much bigger, but it's much harder to budge, and it would take much longer to melt. But there's something like somewhere between 50 and 60 metres of sea level equivalent in the East Antarctic. But, you know, like I said earlier, it would take 10,000 years for that to melt if it got warm enough. But anyway, I don't know if you can see down the bottom the exchange rate here, 360 gigatons of ice. If you melt that and spread it out over the global oceans, which are 360 million square kilometres, you get a layer that's 1 millimetre thick. So even this mind-boggling amount of ice only adds up to about 20 millimetres of sea level by itself. But there's thousands of trillions of tonnes of this stuff on the ice sheet. So there's, in total, somewhere around 70 metres of sea level rise possible. But, you know, it would have to get quite warm, and it would be 10,000 or so years. If we get to 2 degrees of warming, which could happen fairly soon, we might lock in 3 or 4 metres of sea level rise, but even that would take a few centuries to play out. Not that we really want to go there. Okay, next slide. So the question is, you know, what happens next, or how far do we go? Click. Okay, go back to this graph. What we have to do is stop this rise getting much higher, basically. So we know that when we click the arrow, we get a little text box that says this is 1.1 degrees of warming. So this much carbon dioxide in the air gives us a little bit more than a degree of warming compared to pre-industrial. And we know how much we put in the atmosphere every year. We know what the relationship between the total amount in the atmosphere and global temperature changes, so you can work out quite easily, well, when are we going to get to 2 degrees or whatever. So if we click again, we find that at current rates of emission we'll be at 1.5 degrees by about the end of this decade. So, you know, we have basically 0 time left to start reducing emissions. If you want 2 degrees of warming, then we talk another 10 years after that, 2040. 3 degrees of warming comes another 30 or so years after that. So even that's 2070 odd. You know, it's well before the end of this century. So if we don't do anything globally, then we'll be at a level of warming that would basically crash the global economy and would stuff up global society big time. We're talking hundreds of millions of people displaced, probably hundreds of millions of deaths, you know, real catastrophe stuff. And it's maybe not quite within my lifetime. As you can tell from the introduction, I'm an old guy now. I've been doing this sort of thing for a very long time, but certainly my son's lifetime, we really have to avoid that level of warming. 1.5 degrees, hopefully manageable. 1.7, 1.8 also. But once you get above 2, you start locking in some of these big changes, and we really don't want to go there. So if we click again, we find that the amount of emissions that you get from doing nothing for 10 years is roughly the same as getting to 0 emissions by 2050. This is what the IPCC 1.5 degree report pointed out a couple of years ago. So if we can reduce emissions globally by half by this decade and get to 0 by 2050, then it may not be 1.5 degrees, it might be 1.6 or something, but it would hopefully be a sort of manageable level of warming. So the question is, can this be done? And if we click again and see, there has been progress. I guess we all know this, that politically, both in this country and around the world, there's been a lot more talk about what's happening. And this is a bit of an illegal plot here. This is from the final advice of the Climate Change Commission. I thought it was pretty uncontroversial. It's just a bit of history. So here's what some of the big emitters have been saying over the last decade or so, or over the last few years actually. And that the green bit down the bottom, this is Joe Biden's virtual summit just a few weeks ago, where a lot of countries joined in, or the US is back on board, thankfully, and a lot of the big emitters are talking about big reductions soon. It's one thing to say this is what you're going to do, it's another thing to actually do it, but this is fantastic from my point of view. We're really talking the talk now, at least. So we have a look at the next slide. You know, we're talking some pretty significant changes to how things have been going for a long time. So this graphic, this is from the IPCC 1.5 degree report. So what's shown here is the last 30 or 40 years of global emissions of carbon dioxide in billions of tonnes. So we're up at around 40 billion tonnes per year. And to get to 0 by 2050 or a bit sooner if we can, we're talking about, you know, dropping emissions very, very rapidly, on the order of 8% per year, but more than we saw reduced last year through all the COVID-19 lockdowns and things, and we don't want that to happen again anytime soon. And this was put out in 2018, so everything's inched up a bit more, that the slope is even steeper now than it was. And this is the thing, every year we wait, you know, it becomes impossible at some point. Whether it's impossible already, I don't know. But basically the message here is we've got to reduce as fast as we possibly can. There's no two ways about that. Okay, so what about extremes and effects on this country? Click again. Okay. See, I mean, this I've seen a more recent version of this kind of graphic, and it is getting almost to a vertical line, or it can taper off towards the bottom, but we need to see really big reductions in emissions globally immediately. Yeah, okay. So here's some round numbers from a Royal Society report from a few years ago. I'm not saying we'll have 2 more degrees of warming here this century. It's just to give you a feel. So with a 2-degree warming, you get, click, roughly 3 times as many hot days as you had before. So if in summer, typically, whatever you call a hot day, above 30, above 25, if you had a month in summer before, you'll have 3 months. You have the whole summer being hot with a couple of degrees of warming. And then in the dry places, it's getting a bit drier, maybe only 5 or 10% drier on average, but still drier. That gives you, with the warmer atmosphere, click, gives you something like a tripling of the occurrence of droughts. This is in places like Canterbury, Hawke's Bay, Gisborne, and maybe Northland as well, which is another drying region. Put those together and click, and you get a fire season that's 2 or 3 times longer than it was before. And by that I mean that the number of months of the year where you've got either very high or extreme fire danger. So this is, again, places like central Canterbury and Hawke's Bay and so on. And this is a photo of the Port Hills fire near Christchurch a few years ago. And then click again. Sea level rise. I think this is the one that a lot of people think about the most, because it is kind of, seems somehow more frightening than all these other things, or maybe more unstoppable. But yeah, just the message here is that as the sea level goes up, when you have a storm, it's easier for this kind of thing to happen. This is a road in South Canterbury that got partially eaten away about 5 years ago. And it's amazing how quickly the dangers, the occurrence of these events changes with sea level rise. A 10 centimetre rise, this is the coastal engineer's rule of thumb, a 10 centimetre rise in sea level triples the occurrence of any extreme event. 1 in a 100-year event becomes 1 in 33 years with 10 centimetres of sea level rise. Half a metre of sea level rise, it's happening every few weeks. So it's a big deal. And maybe that's why people are worried. And I've got some numbers here, I think, about sea levels. So we've had about 20 centimetres of sea level rise around New Zealand's coast in the last century. We're guaranteed 30 centimetres more in the next 40 years or so. So that 30 centimetres, that's 3 times 3 times 3, that's 27 times the danger. So the 1 in a 100-year event would be the 1 in 4-year event, something like that. And how much we get, it really depends on how quickly emissions can be reduced. So if we can get to 0 emissions by 2050 and stop the warming at well less than 2 degrees, total sea level rise this century might only be half a metre. And over much longer times, a couple of 100 years, it might still be less than a metre. If we don't get on top of emissions quickly enough, sort of the sky's the limit in a way. It could be 5 metres, it could be 10 metres. But this century, over the next century, perhaps 1.5 metres. So it's a range of, I don't know why the text isn't coming up, but oh, there we go. Can you go up, the up arrow? No? No, there we go. Hey! So between half a metre and 1.5 metres by the end of the century, I'd say. That's the sort of range. But beyond 2100 doesn't stop there. The ultimate range could be anywhere between about a metre and 10 metres, 20 metres, you name it. Okay, so if we get that headline back again. So there's been a lot of talk and a lot of thinking about risks, coastal hazards lately, and there's the Climate Change Risk Assessment report that came out last year and various things. So yeah, a lot of people are thinking about this. The insurance sector is certainly thinking about it. I was speaking to IAG a couple of weeks ago, and they're very on to this kind of thinking. And click again, please. Sorry. And yeah, also discussions. I don't know if there's been much discussion here, but certainly there's thinking around, well, how, is this like the Earthquake Commission? Does government have a role to just fund the people who happen to have a house that's right by the coast that might get washed away in the next 30 years? I don't think we can leave homeowners sort of to deal with things themselves. I mean, a lot of people bought a house or built a house near the coast in good faith without perhaps realising the risk. And if their property gets damaged or the infrastructure near their property, like the roads, gets damaged, I don't think it's reasonable to assume that individual ratepayers foot the bill.
Do you think that if that's the case, then at this point, homeowners who have homes on the coast should be on notice about the risks that they run, seeing as this is fairly widespread? Like, at this stage, can you really say someone buying a house, say in Petone, should not be on notice about the risk that they run by buying a property in that area due to climate risks and potential tsunamis and things?
Well, yeah, I think, yes, absolutely. People should be aware of the dangers, and I live on the Kapiti Coast and worked with the Kapiti Coast District Council a few years ago on publicising their new hazard lines on the, looking to the future, the 50 and 100-year risks and where places might be in danger. And as you may know, when those were released to the public, there was uproar, and a group, the Coastal Ratepayers United, took the council to court and had it all removed. So that information is no longer available to the public officially because it's all too frightening, and it would damage property values, right? And these are the most sacrosanct things in the country, as we all know. And that kind of thinking, the Kapiti District Council are having another go now and doing it rather differently, which is good, I think. But we can't just pretend things aren't happening. But I do live on the Kapiti Coast. I don't live right by the beach. But if I did, it's pretty confronting to be told that your house might have zero insurance value in 30 years. You might not be able to resell it, or it might be damaged or washed away in your lifetime. I mean, that's a pretty hard message to hear. So how that's handled is tricky, I think. And it's another reason to start doing the thinking and the managing now. We have to have this sort of managed retreat, basically. And if it has to happen over the next 50 years, we really need to get onto it right away. And some councils are doing things and others aren't. And this is another component of the Commission's advice, that there needs to be a lot more coordination across central government agencies and local government, and a lot of conversation and, regulation and definitions of what should be happening from central government to help local government agencies, which so far have just been sort of left to do their own thing with very little resource, to help coastal homeowners deal with this. And of course, if you don't live by the coast, you probably live on a floodplain and you're at much greater risk of river flooding in future. So there's very few places in the country that get off scot-free from this. So yes, it's a really big question. Anyway, I better finish off or keep moving. So next slide. So here's another, well, this is actually from the new advice, the final version. It looks the same as the old version though. So this is what the Commission's advice looks like, the first three budgets for reductions in long-lived gases, that is mostly carbon dioxide really. So gross emissions in green, net emissions in blue. And it looks as though there is quite a big gap between the two, and yet the focus on of the advice is really to reduce gross emissions. The difference is basically tree planting, and we can't rely on tree planting, it only goes so far. So a big focus is to reduce the actual emissions of carbon dioxide especially, but also to plant trees. And the goal is to get to net zero by 2050. If things work out the way the Commission's modelling suggests, we could be at net zero CO2 by about 2040 if we're really lucky. And if we're not, if certain things happen that in the so-called headwinds scenario, we can still get to net zero by 2050, I think. So if government picks this up and if it all pans out, then this is a pretty good roadmap, at least the start of a roadmap to get us to net zero in the sort of time we need to. So one more slide on that. Yeah. So most of the emissions of the long-lived gases, i.e. carbon dioxide, there's nitrous oxides in there too, but it's mostly CO2, mostly come from the transport sector and the energy sector, so heat industry and power, and that's where a lot of the focus of the advice is. So reducing the use of internal combustion engine vehicles, and most of the growth has been in using cars basically the last 30 years. So converting to electric vehicles, which could be cars, or like me, it could be a bike or a scooter or a skateboard or whatever, but electric vehicles of various forms, and really pumping up public transport, active transport, integrated transport, getting people out of cars, but when they're in a car, making sure it's an electrically powered one rather than a petrol or diesel powered. That's the main message there. And then in the energy sector, it's really about not burning fossil fuels anymore. So getting rid of coal boilers and phasing out Huntly, etc., and your TY and so on are wild cards and all this, but we'll see what happens there. And in the land sector, so for shorter-lived gases like methane, there's less urgency. So the target there, which comes from the IPCC, is to reduce biogenic methane by up to about half by 2050. And there is a great deal of talk about tree planting actually in the advice, but more about natives rather than exotics. So yes, we've got a lot of pine plantations and we'll carry on with those, but we need to move towards native tree planting because they sequester carbon. They grow more slowly. They sequester carbon for a lot longer. All right, one more slide. Well, actually two more slides, but one more real slide. We've gone past. Oh, there we go. So there's this, New Zealand is the first or one of the first countries to bring in legislation around climate-related financial disclosures from the Task Force on Climate-Related Financial Disclosures, the TCFD. And it's not the law yet, but it's going through the process, select committee and so on. And assuming it's passed, then it's as you probably know better than I do, this is about financial institutions, one, identifying and being aware of the things they're exposed to. So you might own infrastructure that's more at risk from coastal erosion, for instance, that kind of thing. Or you might own a forest that could burn down or be destroyed by pests that can now live in this country that couldn't before, all that kind of thing. And also to encourage investment in low carbon infrastructure or low carbon investments of various forms, so climate safe, but also low carbon. So putting money into developments that do not lock in further greenhouse gas emissions. So it's about having the thinking at the governance level and institutional strategy, and then actively managing these kinds of risks. And you have to specify how you're sort of quantifying it all. So that's the basic outline, and it seems like a very good idea. And you know, the finance sector really has a big role to play. The business sector certainly does. Consumers consume what's in front of them, and you know, it's much easier to walk out the door and buy a petrol-powered car than it is to buy an EV. It's becoming easier to do that, but changing the form of what the market looks like, what's available, setting regulation around behaviours that are climate friendly and ones that are not, you know, basically taxing pollution more, all those kinds of things I think are really important. And no doubt the central banks of the world, and I know that the Reserve Bank's part of this coalition looking at, you know, these scenarios for the future for being sensible around how the finance sector operates and how the economy can be shifted in the right direction, basically. It's really good to know. So that's enough on that. I'll just wrap up. I know I've sort of taken a bit more time than I meant. So, summary points. So, climate's changing and, yeah, extremes. I haven't really talked about heat extremes, but they're very important for things like food production. That's another issue that's worrying. But yeah, temperatures are rising, so we're getting more extreme high temperatures, and that's changing rainfall extremes at both ends of the spectrum. More droughts, but also bigger floods. Sea level rise is definitely happening and will be with us for a long time. It's a question of what the rate is. If we can get on top of emissions quickly, then it will be relatively slow. But yeah, if we don't take action globally, you know, there's some pretty scary futures coming that are not that far away. So we need to get to zero global emissions as soon as we possibly can. The New Zealand contribution here is the Zero Carbon Act and the Climate Change Commission's advice. Well, that's part one of the advice that comes out publicly tomorrow. And all the big emitters, at least talking, most of the big emitters I should say, not all, are talking the right talk. Everyone wants to do the right thing. We just actually need to see the change happening. So global emissions need to reduce as rapidly as possible and as rapidly as practicable. You know, you don't want to crash the global economy, and you want the least harm done. This idea of a just transition, I think, is very important. We don't want to further disadvantage people who are already relatively disadvantaged. So thinking carefully about how we do that's really important, while at the same time we go as fast as we possibly can. Okay, that's it. Thanks. You're off the hook now. Thank you.